Hello friends, so to solve this, we use the eigen decomposition of a square matrix. And this states that for a square matrix A, we can decompose this to the eigenvector times a diagonal matrix of the eigenvalues, then times the inverse of the eigenvectors. And we're going to define all these terms here. So A here is our square matrix, Q is the eigenvector of A, and lambda is the diagonal matrix of the eigenvalues. So before we go ahead with this decomposition, let's just do one little exercise. So we have A squared, which is matrix A times matrix A. And if we decompose each of these, we're going to have Q big lambda, Q inverse, Q big lambda, Q inverse. Okay, so this will simply give us Q lambda 1 lambda Q inverse. Okay, and this is simply going to give us that our A squared is simply Q lambda Q inverse, which is simply Q lambda squared Q inverse. Okay, and if you want to solve this inductively for any n, for any number, you arrive at an is equals to Q lambda n Q inverse. And if you can't do this, just let me know in the comment section and I'm going to solve this out, how to solve this inductively. So we're going to use this to solve this problem. Okay, and I will advise you, the first thing you should solve for is your lambda, and that is the eigenvalues. Okay, find your eigenvalues and put it in a diagonal matrix. That might save you a whole lot of time. So let's go for it. And what's the formula used for this? The formula for this is solving this out. The determinant of this being equals to 0. Okay, and we're going to solve this. So let's start by solving a minus lambda I. This is simply our A is 6, 5, negative 7, negative 6 minus lambda I is a unit matrix, which is 1, 0, 0, 1. Okay, and so solving this, how we're going to have that. By subtracting the two matrices, we're going to have 6 minus lambda, negative 7 minus 0, which is negative 7. Next, 5 minus 0, which is 5. This is 0, guys. And negative 6 minus lambda. So we found what this is. Next, let's apply the determinant and equate that to 0. So this will be the determinant of 6 minus lambda minus 7, 5, negative 6, negative lambda. This will be equals to 0. And the determinant, to find the determinant, we're going to multiply this 2 and we'll subtract it from the multiplication of this other 2. So this will give us 6 minus lambda times negative 6 minus lambda. Let me clean this up a little bit. Okay, good. Next, we're going to multiply this 2 and so minus, we're going to multiply this 2. This will be negative 35, and this is 0. Okay, next, let's simplify this. This will give us lambda squared minus 6 lambda plus 6 lambda minus 36 plus 35, and this is 0. So this gives us that lambda squared minus 1 equals to 0. And what is lambda squared minus 1? Lambda squared minus 1 is same as lambda squared minus 1 squared, which is lambda minus 1 into lambda plus 1. Okay, and this is equals to 0. And this simply implies that lambda 1 is going to be equals to 1, and lambda 2 is equals to negative 1. Alright, so we found our eigenvalues. So let's write the diagonal matrix of the big lambda, which is equals to lambda 1, 0, 0, lambda 2. Okay, and this is simply 1, 0, 0, negative 1. Alright, so why I say we should solve for the eigenvalues first is when we have something of this nature and we look at it critically. This is a very unique, this is almost a unit matrix and they have similar behaviors. So let's open up our problems. So since we know that for a square matrix to the power of n, this is equals to eigenvector big N to the power of n inverse of the eigenvector. So the problem we have is also going to be of the form a to the power of 20, 23, 24. If our n is 2024 as we have in the question, this will be q lambda to the power of 20, 24 q inverse. So before we find our eigenvectors, let us first find this and see if our problem will be made easier. So this is going to give us 1, 0, 0, negative 1 to the power of 20, 24. And this is, there's a trick for this. This is simply 1 to the power of 20, 24. 0 is going to be 0, 0 will be 0, negative 1 to the power of 20, 24. Okay? And this is going to give us 1, 0, 0, 1. And I'm going to show you why it's 1 here. So negative 1 to the power of 20, 24, the same as negative 1 to the power of 2 times 1, 0, 1, 2, which is same as negative 1 squared, or to the power of 1, 0, 1, 2. And what's negative 1 squared? It's just 1. So 1 to the power of 1, 0, 1, 2. And this is simply 1. So we have this, our 1 here is correct. Yeah. So this will tell us that our problem 6, 5, negative 7, negative 6 to the power of 20, 24, okay, which should be the eigenvector of this matrix times the eigenvalue diagonal matrix to the power of 20, 24 times the inverse of the eigenvector. And we know what this is already. So this will be Q into the unit matrix times Q inverse. And when a matrix multiplies a unit matrix, it will get back that matrix. So this 2 will give us back Q. Okay? So this is simply going to give us that this is the eigenvector into the eigenvector inverse. And we know that Q times Q inverse is just the unit matrix. So which simply tells us that this problem 6, 5, negative 7, negative 6 to the power of 20, 24 is simply 1, 0, 0, 1. And that is the solution. And we need not find what the eigenvectors are and the inverse of the eigenvector. And that's why I told you, when you have a question like this, first of all, go for the eigenvalues. If it is a unique eigenvalue, immediately do this, and that will save you a whole lot of time during the Maths Olympiad. Thank you very much, guys. And please, if you have any questions, please do drop it in the comment box. I'll be very willing to answer your questions. If you want me to show you how to solve this, I'll be very willing to make a video on it. And just like and subscribe and share. Thank you very much, guys.